This is AP Calculus 6-9 Part 3, and in this section we're going to learn how to integrate inverse trig functions. And part of this does involve completing the square. You may recall a while back we took derivatives of inverse trig functions, and when we did that we had formulas that we had to follow, and those are just formulas you have to memorize for the AP test. Same thing with the inverse trig integrals. You have to memorize these formulas in order to see when you have them. They don't show up real often, just occasionally, but if you don't know these formulas, then you won't be able to integrate specific types of problems. And so just take a minute, write these down. These are the three formulas for inverse trig functions. The first one, the integral of du over the square root of a squared minus u squared is equal to arcsine u over a plus c. U will be where your x or your variable is involved. A is going to be some number. Or if you had a 16 here, then a would be 4. And so you just have to look for these particular formulas. So for arcsine, you're looking for two square things underneath a square root on the bottom. For arctangent, it's du over a squared plus u squared. So you're looking for two things that are squared with no square root. So that formula is du over a squared plus u squared equals 1 over a arctangent u over a plus c. The integral du over u times the square root of u squared minus a squared. And notice this is similar to what this says. The u and the a are backwards, but you also have an extra u on the outside. So when you have that form, the answer is going to be 1 over a arcsecant, the absolute value of u over a plus c. The easiest way to learn these is to just do a few and try to get them in one of these particular forms and then substitute in to get your answer. So looking at this first one, I do have the dx on top. Notice I've got an x on the outside of the square root. So my first thought is this is probably an arcsecant because we've got the u outside and inside that square root. So if I just try to name my u and my a, I always deal with the u part first. My u is the part that has the x in it. So I'm going to say u here is x, because I need to have a u squared, so u is x. I'm going to say that du then would be dx. After we found u, we still have to find du, and so that's what I did here. And we do that the same way we use with substitution. And then my a value, I'm going to say is 1, because this number squared is my a squared. And so then if I just kind of substitute and look at what I've got here, dx is du, so I've got du over x is my u, so that's a u, and then underneath I've got u squared minus 1 squared, right? So if I look at this, that's exactly what I've got here. The only difference is instead of having a, I've got 1 squared. I know that a is 1. So I can assume that this is an arcsecant. So what I would have is 1 over a. Well, my a value was 1, so I have 1 over 1. Arcsecant, the absolute value of u, which is x, over a, which is 1, plus c. And don't forget your plus c. So we got 1 arcsecant, the absolute value of x, plus c as the integration of what we started with here. I've rewritten the inverse trig function antiderivatives up here so that we would have a little bit more room to work. With this one, we've got the integration of dx over x squared minus 4x plus 7. For this, I notice that it does not have a square root underneath, so I'm thinking it's probably going to be an arctangent problem. So what I need to do is I need to get the bottom part so that I've got something squared plus something squared. So, and remember, your u part is going to be the part that has the x value in it. So the only way to get this so that I have two square parts is to complete the square. So what I'm going to do is I'm going to rewrite this as dx over and I'm going to group the x squared minus 4x, leave a little space, and put the plus 7, and I'm going to actually complete the square to force this to be a perfect square. So if I do that, if I take half of 4, that's 2, and if I square 2, that's 4. So half of 4 squared is 4. So if I add 4 here, then I have to do the opposite outside so that I've added a 0, so that I'm not changing the value of what I had here. So x squared minus 4x plus 4, and then plus 7 minus 4, I've added a 4 and then subtracted a 4, so I've really just added 0 on the bottom, not changing its value, just making it look different. And then, if I rewrite that as perfect squares, this would be x minus 2 squared plus 3. So now, this is my u part. I can say that u is equal to x minus 2. So that means my du is the derivative of that, dx. And then my a value, well, this isn't squared, but we could say that it's the square root of 3 squared. So I'm going to let a be the square root of 3. Even though it's underneath a square root, it's still a constant, and we know that the a value has to be a constant. So now if I just substitute in, I'm going to move it up here, the dx is du over x minus 2 squared. X minus 2 is my u, so I've got u squared, plus, that's the square root of 3 squared. That's my a value. So that looks to me like it is this formula. So if I plug in 1 over a is the square root of 3. I've got 1 over the square root of 3. Arctangent, u, my u, we will substitute in just a minute, over a, which is the square root of 3 again, plus c. And then we know that u, the u value is x minus 2. And that is the antiderivative of what we started with. That one is an arctangent. For this one, if we have that 4 on the top, we can still bring that 4 outside. So if I take the 4 outside, I would just multiply my answer times that constant of 4. I'm going to put the dx on top, and then I'm going to try to complete the square on the bottom. I'm going to leave a little blank space there, have the plus 8, and if I complete the square, half of 4 is 2, and 2 squared is 4, so I'm going to add 4 here. I'm going to subtract 4 to offset that so that I've just added 0. And then I'm going to rewrite that as perfect squares. So I've got dx over x plus 2 squared plus 4. Now my u value is x plus 2, so that means du is dx. My a value is the square root of this, which is 2. So you see I've got a u squared plus a squared. U squared plus a squared on the bottom is again another arctangent. So my answer would be a 4. I keep that 4 in the front, times 1 over a is 2, arctangent u, which is x plus 2, over a, which is 2, plus c. And then I could multiply the 4 times the 1/2, which would make that a 2. We can also have definite integrals with the inverse trig functions. So if I were to do this one, first I notice that there is a square root underneath, and that square root has nothing in the front. So when I first glance at this, I'm going to think that it's probably an arc sine, but we'll be able to tell if that's true as we work through the problem. So this time I'm going to work the problem across my board here. I've got still the integral goes from 3/2 to 9/4. I've got the dx here. I'm going to have to complete the square again on the bottom. Now, when I do that, Notice it's in the wrong order, so I'm going to switch it to negative x squared plus 3x. And that's what I'm going to complete my square of. So if I do that, still going from 3/2 to 9/4, I've got the d of x. And if I complete my square here, I'm going to bring out the negative, which means I now have x squared minus 3x. And then I'm going to complete the square. Well, half of 3 is 3/2, and 3/2 squared is 9/4. So I have a 9/4 that I'm adding there. But really, haven't I just subtracted that 9/4 because that negative was on the outside? So if I've really subtracted 9/4 over here, I'm going to then add 9/4 so that all I've done is added 0 underneath that radical sign. So if I rewrite this so that I've got the a squared in front minus the u squared, it's still going from 3/2 to 9/4. I still have my dx up there. When I rewrite this, I need to write this as a perfect square. So that's going to be a negative. I keep my square root. I've got my negative of x minus 3/2 squared plus 9/4. Then, in order to get this one to look the way it needs to, my a squared needs to be in front of the u squared part. So I'm going to switch that around so that it looks like it's supposed to. So I've got dx over the square root of 9/4 minus x minus 3/2 squared. So now if I name my u, my du, and my u is going to be x minus 3/2. My du is going to be dx. And my a value is going to be the square root of this number, which is 3/2. So to sub in to my formula, I do have dx on top, which is the same thing as du. I have the square root of a squared minus u squared here. So I can then plug into my formula. My answer, or the antiderivative, is going to be arc sine u, which is x minus 3/2, over a, which is 3/2. And then we're going from 3/2 to 9/4. And at this point, I'm going to plug in. So I'm going to plug in 9/4 first. So I would have arc sine of 9/4 minus 3/2 all over 3/2 minus arc sine of 3/2 minus 3/2 all over 3/2. So if we do the math, I've got arc sine of 9/4 minus 6/4, which is 3/4, and then 3/4 over 3/2. If you think about what that is, 3/4 over 3/2 is just 1/2. So we've got arc sine of 1/2, and you could use a calculator to do that if you wanted to, minus, here we've got arc sine of 3/2 minus 3/2 is 0, over 3/2 is just going to be 0. So we've got arc sine of 0. So now, how do our arc sine values work? Well, that's the opposite of finding sine of a number. So what we need to do is figure out what angle has a sine that would equal 1/2. In other words, what angle has a y value at the ordered pair that the y value is 1/2? Well, if we go right square root of 3 over 2 up 1/2, that happens at 30 degrees, or pi over 6. So that happens at pi over 6. Where is sine equal to 0? Well, if you look right here, our sine value is 0. Now remember, you should have learned in pre-cal that when you're dealing with arc sine, you're dealing with going from negative pi over 2 to pi over 2. That's your region where you can find arc sine, because that part is a function going from negative pi over 2 to pi over 2. So arc sine of 0, that happens at 0. So we got pi over 6 minus 0, which is just pi over 6 for our final answer. So we can get some of these to be very simple answers, just like in the other types of problems that we've done. So here I've put up another example. Go ahead and pause the video, see if you can get that one on your own, and then I'll come back and give you the answer in a few minutes. Don't forget your plus C. So for this one, first I brought the 8 out, and then I reordered this so that my x squared term is in front. I grouped the first two terms, and then I brought out the negative 1. When I do that, I have x squared plus 4x. To complete the square here, I'm going to take half of 4 and square it, which is 4. What I've really done here, though, is subtracted 4 because of that negative. So out here, I'm going to add 4, so that I've really just added 0 to my problem. Then I rewrite. I have 8 times the integral of dx over the opposite of x plus 2 squared plus 16. Then I switch it around. That is a square root. There's nothing on the outside, so I know it's got to be an arc sine situation. I keep the 8 on the outside. I've got my dx on top, which is the du. I switch it around to 16, which will be my a squared, so a is 4, minus x plus 2 squared. X plus 2 is my u. And then I can sub in to my formula. So 8 arc sine x plus 2 over 4 plus c. So it's really just a matter of manipulating your numbers so that you can get the formula you need, and then plugging in to a formula.